Vision transformer have become one of the most popular alternative to a standard convolutional neural network. It has achieved state of the art in most computer vision tasks. So in this video, we are going to take the advantage of vision transformer and implement an image classifier using the TensorFlow framework. So hello friends, this is Nikhil Tomar and you are watching Idiot Developer. Make sure to subscribe the channel for more such awesome videos. You can also support the channel by joining the membership and also super thanks. Now we are going to take a look at the dataset itself. So for this video, we are going to use the flower classification dataset, and there are 5 classes in this dataset, and these are daisy, dandelion, rose, sunflower, and tulip, and each folder contain images inside them. Here you can see some of the sample, and if you notice the height and width, they changes, so there is no fixed size for the images. You need to choose a size for yourself, and for this task I'm going to use the size 200 by 200. That is what I feel is more appropriate for this data set. Okay, so this is about the data set itself. Now we'll start with the implementation. So here we are in our atom text editor. So first of all, we'll start by implementing all the files which we require. So let us implement some of the files. So here we have first of all imported the OS library. After that we have set this environment variable, that is tf_cpp min log level. So this is just to make sure we don't have that TensorFlow message, which whole lot of messages appear before running any program. After that we have the numpy, then opencv, globe, then shuffle function from the sklearn. Then we have train test split to split the data set into 3 different sets, that is training, validation, and testing. After that we have a library called patchify, because if you have studied transformer even a bit, you know that transformer do not take whole image at once. The image need to be converted into patches, then their patches are flattened and then given as input to the network. So that is why we're going to use this library called patchify. So it would help us to convert the whole image into patches. So now we need to set some hyperparameter, and we are going to set those hyperparameter at the starting. Okay, so this is a bit long. So first of all, we have this empty dictionary called HP. So HP refers to hyperparameter. So first hyperparameter is image size. So the image size is 200 by 200. So it's gonna be an RGB image. So we have 3 channels. Next we have a patch size, that is 25. So try to make sure that patch size is a multiple of this basically. It's gonna be, so when you divide the patch size by this, so this should not give a remainder. So I hope you get the idea, because we need to divide the image into patches, so all the patches should be of equal size. So that is how we're gonna have the image size and the patch size. Next, number of patches. So number of patches is equal to the image size into image size divided by patch size into patch size. So this is a simple formula, and after that we need to flat patches shape. So that is basically this shape is going to be the input for our ViT, that is vision transformer. So this is, first we have number of patches, after that we have patch size and number of channels. So I'll explain this with another example. Okay, so this is one slide and this is the example for this video. Okay, so image size is height by width by number of channel, and here we have an image of height 200, width 200, and number of channel 3. Then we have patch size, that is 25 by 25. Then we need to calculate number of patches. So number of patches would be 200 into 200, that is height and width of the original image, divided by the height and width of the patch size, that is 25 by 25. So after calculating we have 64 patches. This is gonna be an 8 by 8. Okay, so if you take whole image and divide them into patches, so we have 8 patches in row, 8 patches in column, so this total makes up to 64. Now we need to transform this input, those patches, and give them as input to the vision transform. So this would be number of patches, that is 64, then patch size, that is patch height into patch width, and number of channels. So this would make the shape of flattened input as 256 by 1875. So this is just a simple example. These height and width can change, these patches can change. Just remember these formulas. The number of patches is height and width of image divided by the height and width of patch. Then transform input is number of patches, comma, patch height into patch width into number of channels. So this is how you're going to transform image into the flattened patches. So I hope this is this part is a bit understandable for you now. I'll explain when we move on to the image processing part. Now let us set some more hyperparameter. So first is the batch size. Here we'll set a batch size of 32. So this can be less or more up to you depending upon your GPU capability. I'm using an RTX 3090 which has 24 GB VRAM. So I can easily handle this much batch size. Then we have learning rate, that is 1e minus 4. Number of epoch 500. This is just an example. You can run it to 50 or it's up to you. Because I'm going to use an early stopping mechanism, that is why I've set 500. Number of classes, here we have 5, and the classes name are Daisy, Dandelion, Rose, Sunflower, and Tulip. Okay, now let us work on the data set first. So we need to extract that data and split it and do a whole lot of stuff. Let us move on to the main part, the main function. So first of all, we are going to seed the environment. So we have not imported TensorFlow, so let's import it, and then we're going to seed that also. Okay, so here we're going to say, give some space, tf.random.set seed, that is 42. So we have seeded the environment. Now when during training we need to save some files, and we're going to save those files inside some folder. So let's create a function which is going to help us to create a directory or an empty folder. So we're going to call this function create dir. It's going to take the path where we need to create the folder. Okay, so first of all we're going to check if that path exists or not, and if it does not exist, then create that folder. If not, os.path.exist, then os.make dirs path. Okay, so this function would help us to create blank folders. Now let's create a blank folder called files. Now let us set some paths. First would be the dataset path. So this can be different depending upon your computer, and this is the path for my system. As I'm using an Linux system, basically I'm using an Ubuntu 22. So this is what my path looks. If you are using Windows, this can be different for you. So if you are a Windows guy, so this slashes would, this path can cause a bit problem. So just make sure and print every time if this work with path, print them, be confirmed that the path is appropriate. Okay, because this is the most common error which I've encountered with people who are running my program on Windows. So they encountered error, and this the most of the time the error is around the path only. Okay, so just be sure. So next we have two more path. Okay, first is the model path, so where our weight file is going to be saved. Second is the CSV path. So this is a CSV file which is going to log all the activity of the model during training. Now we're going to move on to the data set. Okay, so we're going to write a function called load data, and we're going to give it the dataset path. So this function is going to take this path and is going to extract all the images and split them into training, validation, and testing images. So let's start with it. First we need the path and is argument called split with the value 0.1. So 0.1 basically indicate that from the complete data we're going to use 1% of the data for testing and another 1% for validation. So it's going to be a split of 80-10-10. 80% training, 10% validation, and 10% testing. So the split value can change, it's up to you. Now let's move back to this folder. So if you see this flower folder, inside we have 5 different folders, and inside each folder we have multiple images. So let us extract all those images. Okay, images. Next we're gonna call globe, and we're gonna give some path here. Most of the time I'll try to use os.path.join to make sure that it is independent of the operating system, because in Linux we use these slashes, and like in Windows we use I think those or double slash. Like I'm a bit confused, so just make sure it is appropriate. So first we have this path, this main data set. Next we have 5 folders, so we want to extract images from all the folder. Next we want to extract all the images which are ending with .jpg. Okay, so if we see we have 5 different folder. So what I'm going to do, I'm going to shuffle the list here, because this images is a list. So this globe function give you a list, so I'm going to shuffle it just to make sure that then data scrambles, because when I split it, it should not split like the daisy or the first class is in training and the last class is in testing. So this is going to confuse the model and the performance would go really low. Okay, what you can even do furthermore, you can take the individual class image and split them into 80-10-10 and then combine all the training images from all the 5 classes. This way it's going to be much better, but for this video we are not going to do that stuff. We're going to remain simple, just load all the images, shuffle them and split them. So that is going to be a much simpler approach, but it can lead to some data imbalance between the training, validation and testing. So next we're going to calculate the split size. So how many images would be 1%? Okay, so number of images would be integer, then we're going to say length of images multiplied by the split. Okay, so let us print this list images first, and then we're going to print the split size. So let's run this program. First of all, we're going to get a list. This is the list of all the path, and we have 431 images. So this is basically 1% of all. Okay, we are done. Now we're going to split it. Okay, so first of all we're going to say train x valid x. So first of all we are going to split this all images into training and validation. So here training would take 90% of the data and validation would take, okay, the training would take 90% of the data and validation would take 10%. Now we're going to have a train test split function. We're going to give the images, then we need to give the test size. The test size would be equal to split size, that is 431 images I think. Then random state would be 42. Just make sure use a random state so that you have same split every time. Okay, next, so now if you see we have 90% data in training, so we're going to again extract 1% as test set. So we are going to copy this and paste it here, and instead of images we're going to write training axis. So let me zoom out a bit. Okay, so we have now training, validation and testing. Let's give those value back. Okay, let's get a bit down. Okay, let me. So we have train, validation and testing. So let us print them and see how many sample do we have for all the three set. So let me just clean the screen, run it again. So you can see we have 3455 images for training and 431 images for validation, and again 431 images for testing. So we have loaded the data and split it. Now we're going to work on the dataset pipeline. So this is basically the tf.data API which we're going to use to train our model. So for this we need to write some simple functions first. Okay, so first of all we're going to write a function where we're going to take the image, okay, image path, individual image path, and we're going to process it, and we're going to read it, and then we're going to convert it to patches, and also we need the label. So we're going to convert it into label also, because if we remember the path, this path, if you see there's a lot of path, this tulip is basically the class, so we're going to extract the label from the path only. So let's work. We're going to call the function process image label is going to take the path. Okay, so let me just call this function for now here just to test. It's going to take an image, we're going to give one simple image. Okay, now we are just calling it here just to test whether it is working or not. So first of all we need to read the image, so we're going to call image equals to, here we're going to use open cv2.imread. first it's going to take the path, then we need to read it as RGB image. Now let us resize the image. While resizing we first give the width then height, but here because both height and width are same, so we need not to worry about. But just remember, first it is width then height. Like even in the starting I'm confused, so some of my program won't run that, give an error. So now let's normalize all the pixel value by dividing them with 255. Okay, so this is, like we can say, reading images. So let me just write it down, reading images. So now I'll print image shape. You can see it's 200 by 200. Okay, and 3 as the number of channels. Now next we're going to convert it to patches. So pre-processing to patches. So first of all we need the patch size, patch shape. Okay, patch shape. Patch shape would be hyperparameter dictionary. First patch height, so here also height and width are same, and patch width, then number of channels. The number of channel are 3. Okay, so this is the patch shape. So now we're going to use our patchify function which we have imported here at the above function, patchify. So just first give it the image, okay, which we normally read as height by width number of channel, then give it the patch shape, okay, in which you want to convert it. Then next we have a step basically. So from you want to have patches, let's say from 0 to 25 pixel, then next patch should from where it should begin, it should begin from 26, I think. Yeah, 26. Okay, 0 to 25, then 20 or 0 to 24, like it's a gap basically. So here we need to give the patch size. So that is basically the step after which it begins cropping the patch. Okay, so I hope you get my point here. So now I'll print the patches. Okay, here I'm going to print the shape. So if we remember, how many number of patches do we have? If we go above, okay, here, okay, I remember it's 64. Yeah, not written here, but it's 64. Let's see. Here you can see 200 by 200 original image. Then we have this patch. It is 8 by 8, that is 64, and then 25 by 25 by 3. So let us, we can reshape it, okay, accordingly. So we need to reshape it to this, remember, flat patch shape. Let's do it. Let's, if you also want, I can, okay, let us first, before this, there's this reshaping them, let us save those images. So first what I'm going to do, I'm going to multiply all these. So let me just reshape them for once. So first would be, I remember 64. I'm just manually putting the value. Then 25 by 25. 3. So for I and range 64. Okay. So we're gonna save the value. Let's, so we have this folder files. So we're gonna save all the patches inside that one. Okay. cv2.I am right. So this is the function from OpenCV library to save an image. Here we're gonna save the image patch. Patches I. The name of the image. I think first comes, yeah, first comes the name. Right. First comes the path, then the array. This would be files slash I would be the name, and they would be in PNG. So let's execute it. Okay, it's done. Now let's go to our folder. You can see we have our files folder. Okay, inside it, okay, we have the patches, but they are black because we have normalized the image. So let's not perform this step. So program is done. Now I can see, okay, I'll zoom it. So if you see, we have this flower. Okay, I know how you can see it correctly. So this should be, it is 8 by 8, so this should be, okay, I think now you can see the flower. Yeah, you can see the flower, complete flower, and we have these patches, and these start from 0 to 63. So we have in total 64 patches. So this is how you're going to convert them to patches. Okay, so we are done with patches, and I've shown you. So let me just remove this part. I'll just comment it out so that later you can see it. So what I'm going to do now, I'm going to flatten those patches into an appropriate shape. Patches, the shape is in hyperparameter flat patch shapes. Okay, so we are done. Now we need to provide them a data type. So these would be in float 32. I'm just explicitly specifying because we need it, we need to know the value of the data type. So that is why we are explicitly defining them here. So now this patches part is done. Now we're going to move on to the label. Okay, so label, the name of the class is in the path only. So first of all, let's print the path. Okay, now we're going to print the path, and we're going to extract that class label. So this is the path. Okay, now if we start from last, there would always be the see, whatever your data set where it is stored, it does not matter, just start seeing this string from the last. So in the last, first we have is the name of the image with the extension. After that we have the class name, so we need to extract this. So this sequence would not change wherever your data is. This is going to change, but this sequence is not going to change. Okay, so if we see, these strings are separated by these slashes. So let's pick one slash, and what we're going to do, we're going to call a variable called class name, and we have path dot split, and we're going to paste this. Okay, and now I'm going to print class name, and see, it would give you a list where all these words are splitted. There you can see we have split those words into separate item in a list. Now we need to extract the second last. From the last, if you see, it is second, so we're going to say -2, and now we're going to have our class name. See, here class name. So as you can see, this is the sequence: first daisy, dandelion, rose, sunflower. So what we're gonna do, we're gonna give an index number 0 to daisy, dandelion 1, rose 2, 3, and like this. So we have already have a list of the classes name. Okay, so what we're gonna do, we're gonna have our class name, we're gonna index this list, and we're gonna get the index number, and that is what our label would be. So we need to get the label class index, and this would be, first we need classes name list. Whether it is class name or class names, let me check. It's class names. Okay, class names dot index. Okay, here we are, and then we need to give the class name. So we're gonna get the class index. So our class name is dandelion, and it should have an index value 1. So let's check. You can see index value 1. So we have splitted the path, get the class index. So this index is basically the label for this. So from here we're going to give these two things back. First is the patches, that is the input, and second is this class index. So this processing part is done. Okay, now we need to write some function. We're going to remove this, we don't need this now. Now if you see, we are using OpenCV, NumPy, and whole lot of things, and these are not included in TensorFlow. So these are outside the TensorFlow. So to use this function inside the TensorFlow, okay, I need to use a function in TensorFlow called tf.numpy function. So let's work on that. Okay, before that we need to specify a data type to this also. So we're going to say num array, and we're going to convert it to integer 32, because we explicitly need to know their data type, and that is what we're going to do. So we're going to call a function called parse. So it's going to take the path. So we're going to call the function called tf.numpy function. First of all, we need to give the name of the function which you want to execute in the TensorFlow. This is the input would be path, and now here we need to specify the output data type. First would be float 32 for the patches, next would be integer 32 for the labels. Okay, there we can say we have patches, and we're going to call them labels. Now we need to set the shape. Okay, before setting shape, the class index of the label is not in one hot vector, so let us convert it to a one hot vector. So one hot vector is basically, let's say here the class index is 2. Okay, so this would get converted into 0, then 1, then 0, then 0, then 0. Okay, so these are 5 class, and for each class its respective index would be 1 and rest would be 0. So this is a one hot vector representation. So this is basically sparse representation where we have more zeros and less of one. Okay, this is just to balance them, because 1, 2, 3, these are increasing order value. So 1 is basically 1 unit, 2 is basically 1 plus 1, so it is much bigger than 2. Okay, so this would cause a problem while training, especially in loss function would be high if we do not standardize those values. And that is why, if you remember, we normalize all the pixels here just to standardize them in the range of 0 and 1. Let us remove those. Okay, so let us return back. So we're gonna say one hot. Now we need to give that vector and the number of classes. This should be HP hyperparameter num classes. Now we can see the easiness of specifying the hyperparameter at the top. You can call them anywhere. Otherwise, you need to call them as a function argument, and that would take a whole lot of work. So it's better to define them at the top and just get things done. Now we need to set shapes for these patches and label. So if you remember, the shape for this is this. Is resized to flat patches shape. Done. Then labels. The shape for the label is num class. It should be number of classes. Okay, I'm gonna wait here. It should be num classes, not class name, and we're gonna give those two value backs, patches and labels. So this is done. Now we have one more function in the data processing part, tf.dataset. So it's going to take the images. These images can be from training, validation, or testing. We specify batch size here, call it batch only 32. This is the default value. Okay, next we're going to use tf.data API here. A tuple of images. So now we need to process. Here we're going to use this. So first of all, we need to say path is equals to path.decode, because now this function is going to get through the TensorFlow. So this path is going to get encoded. So first of all, we're going to decode it, and then we're going to work. So we're going to say map here, and we're going to give the name of the function, that is process image label. So what happened is, from this list of images is going to give individual item to this function, and it's going to give the patch and labels to this, and it would automatically create a batch using this batch, and after that we're going to have the prefetch. Prefetch is basically, let's say if one batch is in training, is in processing, then you can get some prefetch some batches in advance. Let's say we want to fetch 8 batches in advance. Let's say 8. I don't know what value would be suitable. Let's set it 8. If there's an error, we can change it. So now what we're gonna do, we're gonna have our this dataset API, that is train dataset. So we're gonna say tf dataset. We're gonna give train x, that is train images. Batch would be equal to hp hyperparameter batch size. Then valid ds tf dataset valid x, that is validation images. Then batch size would be, copy it from here. Okay, so these two things are done. So here we do not apply any data augmentation. We're going to train them just in this way only. We can use online data augmentation or offline data augmentation for further improvement. Okay, so let us try to run this for xy in train ds, and now I'm going to print the shape of x. X refers to image and y refer to the label. I'm going to break this loop here. I'm just doing it just to show you. Oh yeah, there's a big mistake I've done. There's one more function here. I forget. From tensor slices. As I'm using PyTorch for a lot of long time, I just basically get confused. Okay, tensor object has no attribute. Okay, let's go back and see what mistake we have done. It says this does not work, and I'm confused why this does not. So let's comment it out and now print the path what it is, because this should not be an error something like this. I am writing this code a lot of time, and from my experience, can't convert object to string for file name. So let's see the error. So this is of type string, and I don't know what is happening here. It's a bit confusing thing. So this should not give an error like this. Okay, I'm a bit confused. Okay, we'll solve this. Don't worry. We'll solve this, and it would definitely get solved. So let's print this path, because first of all, this parse function is called. This is the error. We need to give this parse function here, not this process image label. This is the simple mistake what I am doing. Now it would work. See, this would definitely work, and you'll also know the reason why we put path.decode. You can see path, and if you see, they are encoded. That is why we need to provide. And here you can see the shape, 32 batch size, 64 number of patches, and that is the flattened patches, and this is batch size and number of classes. Let me remove this. So we are done with till this part where we have everything ready. We just need the architecture. Okay, here we have our model. So now we are going to implement our vision transformer. So let's do it from scratch. Okay, so if you have already watched my video on ViT implementation, then it is okay. You can skip this implementation part. If you are new to, then please just go through this. Okay, let's start working on this implementation of our ViT, that is vision transformer. So before going on to the implementation, let's just have a look at this simple presentation, or you can see the slide. Okay, so this is a simple slide. So we're going to implement the vision transformer, and this is the architecture. Okay, this is really simple. So first of all, we take the whole image, divide them into equal size patch. Okay, and we have these patch in a sequence. So we give these patches to a linear layer, or you can say in TensorFlow a dense layer. Okay, and we get some embedding, and we call those embedding as patch embedding. Okay, so we know we are this is a patches, this is a part of whole image, so we provide them with a position embedding. Okay, so this position embedding began with 1, 2, and it goes on. So here we add both the patch embedding and the position embedding. You can see here we have the combined patch and the position embedding. So we give position embedding just to retain the positional information, so that the transformer knows that this is the first one indicate the top left part, and the last one indicate the, so it basically just to have the positional information. And after that we have an extra learnable class embedding. So this 0 here basically indicate a blank embedding here, which is learnable over time, and we give all that as the input to this transformer. So now what happen is, we have in lot of output, like here we have 10 sequences, so we have 10 different output for the transformer. So for our image classification task, we take the output of this class embedding. Okay, because it's going to learn the image representation over the 10 transformer encoder. But the question is, why don't we use any other? We don't use any other output because in this way we are biased toward a specific patch. Let's say we take this patch 4. Okay, so this, in this we have a different thing. Okay, and we are going to be biased toward this, and if you see other patches it would have different information. So this extra embedding is going to learn a general representation of all the patches, and in this way we are also not biased toward a specific patch. So this is about the architecture. So you have already understand the input processing, how we transform this image into patches. Next we have this theory and example which we have already done, and now this transformer encoder. So it is just a simple encoder which began with your embedded patches. It first passes through this normalization, and here we use layer normalization. After that it goes through the multi-head attention, which is one of the most essential part of the transformer. Then we have a skip connection, or you can call a residual connection. Then it is followed by a layer normalization, then a MLP. So in MLP we have two dense layer, and in between we have a GLU activation function, and again after that we have a residual connection, and we have like n such encoder. Okay, we have a number of such encoder. Now ViT variants. So we have three different variants for the vision transformer, that is ViT base, ViT large, and ViT huge, and these are their parameters. That is how many layer they would have, what is the hidden size, what is the MLP size, what is the number of heads, and these are the total number of parameter that each architecture has. So in this video we will use the ViT base for the image classification, and I think that too is really large for image classification. You can decrease them accordingly, but for this video we are going to have this ViT base. You simply just need to change this configuration and you are done. So let's move back to our code. So we are going to implement this ViT. So first of all we need the configuration. Let's call our main function first. So we need this configuration of this image size and every other thing. Okay, so here we have this config dictionary, and inside it we have defined all the things. So for now, let's say these are our parameter. Here we have a number of patches as 256, patch size 32, number of channel 3. Okay, so this is just an example. So let's define a function called ViT, and it's going to take this CF configuration file. So first of all we need to define the input shape. So first of all it would take number of patches. Then it would have patch size into patch size, that is patch height into patch width, number of channel. So let's just do that. I'll straight away copy it here. So I hope you just understand the concept of input shape, how we take the entire image and flatten it and give it as the input of this net. Now let us define the inputs layer. So let's print the shape of this input layer. So I'm going to show you the shape of each layer so that you also know how are we proceeding. This ViT, we're going to give this config to this function, and we're going to run this ViT. You can see the input layer has this shape. None refers to batch size, then 256 by 3072. Now next what we need to have is patch plus position embedding, and let me also write here it is the input layer. So these small lines help you to know how we are proceeding. So here we need first patch embedding. We're going to call it patch embed. For this we're going to use a dense layer and we're gonna give a number of features, number of output feature, and that would be 760. That is hidden dimension. So we're gonna call CF hidden dimension. Thus that is done. And now we need to give it the input. Okay. So we are not going to use any activation function here. No non-linearity is going to be applied straight away. Just we need some embedding or features. That is why we don't apply any activation. Let's also print the shape of this layer. That is patch embed. Let's run it. And now we have converted these 3072 features into 768. Let us copy them straight away and paste them here. So we are done with patch embedding. Now we need position embedding. So for that we're gonna have a sequence of numbers starting from 0 to, we have 64 patches, so 0 to 63 positions. TF dot range, we're gonna start with 0. Limit would be equal to number of patches, and the end, not the end, the step, like from 0 to 1 3, how many step in between, the difference in between the first and second would be 1. So it would be 0 1 2 3. So let me just print this position for you so that you also know what it is. So you can see from 0 to 255. Okay, the number of patches changes. 64 is just for this. I'm confused. So here number of patches, if you see, are 256. Okay, so it would be from 0 to 255. That is 256. It's right. I'm incorrect. I'm sorry. I'm just mixing two different things. Actually, this code is from the old video. I'm just redoing it again. Okay. Now we need position embedding. For that, we're gonna use the embedding layer. So input dimension for the embedding would be number of patches. And the output dimension would be hidden dimension. And we need to give an input to this layer, that would be positions. Okay, so now we have this patch embedding and the position embedding. So let's, before that, print the shape of this position embedding. Okay, my mistake, it should be embedding, not embeddings. This autocomplete sometime give an error. Again, these are just like simple mistake when you don't know things correctly, but that is not an error. You cannot know everything. Just you get the error, you solve it. That is fine. That is enough. You just need to know how to solve them. You don't need to learn every function and every argument. So that is, you can't do. Okay. So now we have patch embedding and the position embedding. So now let's join them, and we're gonna call it the embed. Patch embed plus position embed. So let's print its shape, embed dot shape. You can see none refers to batch size 256 by 768, and this is the size. Okay, this size would remain same in the entire transformer network except the what do we have, that MLP. If you go back to our, so the embed patch would have this specific shape basically, and when it comes through this output, it would have the same exact shape. Okay, what happened, it's inside, it's remain inside, just the input and output shape would be same, and that is what we have here. This specific size would remain same here at the end of the transformer encoder. So now we need to add a class token. We're gonna say adding class token. Okay, so for this we're gonna define a class, and we're gonna name this class token and the input would be embed. Okay, so let's call it for now. Let's build that class. Class token. So this class would be a layer, like the layer we have a tons of, like the input layer, embedding layer, that kind of layer. So we need to define the initializer, self, and the super statement, because this is an inheritance. So I hope you are comfortable with object OP concept. So here we have build function. It's going to take the input shape. Then we have next function called call, and here the execution begin. Okay, so this is the basic structure of a layer. So inside build, we need to define some variable, the weights we define here. So first of all, we're going to define an initializer, because if you go back here, this is extra learnable embedding. That is what we are working on. So this is going to be learnable. So we need a variable, and we need to initialize that variable, and we can initialize it randomly. So you can initialize it, let's say, with zeros, with one. Our variable would be self.w, then tf.variable. First we have an initial value that is defined by this weight initializer, and inside it we need to give it a shape. So first of all, let's give it a shape. So first would be 1. So here 1 represents the batch size. Okay, then 1, because we need one extra embedding here. Okay, see, this is the size, none, 256 by 768. So batch size, we just putting it as 1 here. Just forget it now, just don't confuse with that y1. Just go with that. Just 1 is defined here, that's okay. And here we need one more, so we need one more. So that would, if we added 1 here, it became 257, and this would remain same. So it would be 1 by 1 by input shape minus 1. Okay, this is the initial value, and we need to give a data type. It would be tf.float32. Next, a variable called trainable. This is just make sure that it would train, it would change over time. So this is the weight, or things, this is the weight, or we can say the class token which gonna learn the learnable embedding. Okay, so first of all, we need to extract the batch size from this inputs. So that would be tf.shape inputs 0. Okay, then we need hidden dimension, and we can extract it from this dot shape -1. Now we're going to use a TensorFlow function called tf.broadcast. So with the help of this function, we're going to properly shape it. That is this self.w to batch size by 1 by hidden dimension. So it would become none by 1 by 768. And then we're going to change its data type, and we're going to give this value back. So this is our class token. I think it's really simple. It's not that complicated if you understand it a bit. Initially I was also confused, but then I refresh my concept about like making classes, making layers, new layers. So let's say this is the token. So now we need to concatenate it. So we're going to say x as the output, the concatenated output. Concatenate. First we have this token, because token is added to the starting of the sequence. Okay, just again let's have a look at the diagram. So this is the token at the starting, and from after that begins the patches. So this would be embedding, and this is on the axis 1. Let's print shape You can see it became 257. That is what I'm saying at the starting before we start working on this class token. Okay, so we are done with till this part. Now we need to work on transformer encoder. So inside it we have this transformer encoder block and we have this MLP block. So first of all, let's start working on the transformer encoder. Let's build some functions. Transformer encoder. So it's going to take the input, the previous feature map or the embedding, then this configuration dictionary. So just go back to this diagram. So first we have this input. So this input also act as a skip connection. So first of all, let's save it. Call skip 1 equals to x. Then it is followed by layer normalization and multi-head attention. Layer normalization, input would be x. Then it is followed by the multi-head attention. So this multi-head attention is already implemented by the TensorFlow. We need to give it number of heads, that is CF num heads, then the key dimension, that would be CF hidden dimension, and we need to give it the input as x, that is 2 times. Now after multi-head attention, we are going to add the output of multi-head attention and the skip connection. X add x and the skip. Next, let's go back to the diagram. So you can see that after adding we have this output, and this output act as a skip connection, the second skip connection. Let's do this. Skip 2 is equals to x. After skip connection, we again have a layer normalization and an MLP block. Let me just copy it here. Next we have this MLP. So I haven't defined that function, so we're going to define a function called MLP, give it the x as input, then CF, and after that we're going to add them. So now just imagine this function is built, okay, and just continue the flow. Skip 2. Let's go back to this. So we are done now. This is the output. So here we're going to give this x back. So now we need to build this simple, what do we call this, MLP function. It's going to take the input, then CF configuration file. So first it has a dense block. Okay, now the output number of feature would be MLP dim. Then here activation is equals to GLU. Input would be x. Then we have a dropout here. Let us specify the dropout rate. X would be input. Then again we have a dense layer. And here the output number of feature would be equal to input number of feature, that is hidden dimension. And no activation function is provided. And again we have a dropout. So this is our simple MLP. Okay, so this is really simple. It's not that difficult for you. If you are studying about the transformer, and building this is really easy. Okay, so now let's back to our ViT. So now we are done. We have this concatenated output. We have built the transformer encoder function, MLP, and a whole lot of things. So now let's start working on it. Let's build this transformer encoder. Okay, and it is repeated L time. So here number of layer is 12. So we're gonna say for underscore in range. So we're gonna have a loop num layer times. Okay, so we're gonna call transformer encoder. We're gonna give x, that is this concatenated x, and then configuration file CF, and the output should also be x, so that the same variable again goes back and it is repeated. So now let us, this is the output. Okay, so this is the output of the transformer block. this entire block or architecture, you can say. Let's go back till here. So we have built till here this transformer encoder. Now we are just printing the output of transformer encoder. Now see, this is the input shape, and that is going to be the output shape only. Input and output would be the same. You can see this is exactly the same shape we have. So if you see, we have this one extra embedding we have added, and then we have 256 number of patches. So now we need to extract this one extra learnable embedding for our classifier. First we have a layer normalization, then let's extract that one extra learnable class embedding we have added. So first is the batch size. So we do not want to touch with the batch size, so it is going to remain as it is. So this is kind of slicing we are doing here. Next we need this 256, 257, 0. The first index number we need. Then we're gonna have the number of features we don't want to touch. It's gonna remain the same. Okay, so this way we have extracted. So I'm gonna print it. Okay, let me just copy it. Not because these both are same. So let me print them here. Now we're gonna have the shape of this sliced. So this is none by 768. Now we're gonna use this feature for classifier. We're gonna have a dense layer, and we're gonna call CF number of classes, that is 5. Activation is softmax because this is a multi-class classifier. Model equals to, because we now have both the input and the output layer, so we're gonna build the model and give this model back. So we have implemented our ViT, that is vision transformer. So I hope this is really simple and you are able to understand it. Okay, so if you have reached this part of the video, then please make sure to subscribe the channel and hit that like button for the work I'm doing, just to encourage me to do more work, because each of your like is like a motivation to me. Like, it helped me to build more video. Like the last video you gave a good amount of support. Okay, and I'm really thankful for that, and because of that support only I'm just motivated enough to do this, implement the same thing. It's basically the same thing I'm doing in this ViT implementation, just the image classification part is a bit different. So just make sure to subscribe the channel and hit that bell icon. Okay, now let's run this finally, this ViT file, and see the summary. We have some errors. Num classes do we have? Okay, we don't have num classes, so let's add it. We do not have here because we have 5 classes, so let's by default give it 5. Let's run it again. Okay, finally it's done, and as you can see, it is none 5. So it's a simple classifier we have built at the last of this transformer decoder here. So this is the ViT which we have implemented. Now let's move back to our train file and let's call yeah, from ViT import ViT. So that is ViT base. I think this is the function name. Let me check. Yeah, this is the function name. So let's first now work on the model. Model equals to ViT. We're going to give it the hyper parameter file, that is the configuration it requires. Next we're going to compile the model. The first is the loss function, because we are working on a multi-class classification, so it would be categorical cross entropy. Next is the optimizer, that would be tf.keras dot optimizers dot Adam. Here we need to specify the learning rate. Let's also set a clip value. Let's set a metric accuracy. So for this, we're going to use an accuracy as the main metric. Okay. So next, we're going to define some of the callbacks. So we have 4 callbacks here. First is model checkpoint. So it saves your wait file when your validation loss it starts to reduce, starts to decrease. Then we have a reduce LR on plateau. So it decreases your learning rate when your validation loss stops decreasing. Next we have the CSV logger. So this is basically help us to create the log file which would contain our training, loss, accuracy and everything. And last is early stopping. So this early stopping mechanism just it monitor your validation loss. So if for a continuous 50 epochs, if your validation loss does not decrease, it stops the training. Now we're gonna finally call our model.fit function, and that is the end of each of the training file in the TensorFlow. Now let's run this. Okay, we need to run the training file. I hope this would work. Oh, hidden dimension. Let's see the error where it is. Oh, I know the mistake. We haven't defined those configuration here. Okay, let me just directly copy them here instead of writing them. Okay, that is a mistake. Here, number of layer, hidden dimension, MLP dimension, number of head, and the dropout. Okay. So this is for the base configuration. You can change them, and the same architecture is gonna be like ViT, huge ViT large. Okay, so this is up to you how many number of layer hidden dimension you require. Let's say you're working with really small data set like I am, so you can decrease it. Okay, it's not compulsory, it's up to you and your task. Again some error are not a problem. The problem is if you don't solve them. So let's, I think it's model.compile, I believe. Yeah, model.compile, invalid argument, compile. That is strange. Compile is not an invalid, it's model.compile. Let me check the spelling. COMPILE. It is correct. We have loss. It's optimizer, not optimizers. See? A small spelling mistake can stop your program. Again. I forgot to import them because I directly copy paste things. That is bad. See, you cannot remember the whole code. You have to see it somewhere and do some things. So I just have a simple file on opening on my second desktop. From there, I just take it as a reference. Okay. Otherwise, the video would be really long in solving error. Okay. Okay. Now you can see the training begins, and I think it's gonna get good accuracy. So till the time it's trained, let us build the test file. Okay, and we're gonna let it train. Okay. So for testing, we're gonna copy some things from our training file only, because those things are going to be repeated. So first of all, we import the libraries which we require till TensorFlow. Then we have this from train. We import these two functions, load data and the TF data set. We also import this ViT. Then we have those same hyper parameters. Just don't change them. Okay. Then we have our main function. Let me call it here. So inside the main function, we first have the seeding. We put the same seed number. Okay, just make sure you have same seeding number. Then we have dataset path. Next we have the model path. Okay, now we are going to load the dataset. So here we have our test images. So we're going to build our test dataset. And here we need to give the batch size. Now we need to load our model. So this is also going to be the same. Model is equals to ViT. Our configuration, that is hyperparameter file. Now we need to load the weight here. And this is where our model path would come handy. See, okay, so few epochs are done and this is working fine. We are having an validation accuracy of 46%, and that is not bad within 3 epochs. So let's continue working, and finally we're going to see our validation, this testing accuracy. So we need to compile our model, and now finally we're going to say model.evaluate and test dataset. So this is just, we are done. Okay, let's just let it complete this 4th epoch. So we're going to stop it at 5th epoch. Let it done with the 5th also, and then we're going to stop it and see how much performance we get within just the 5th epoch. So you can train it more to get more performance. You can also play with those hyper parameters, okay, because your model is really huge and you don't have those number of images. Okay, so this is not good because you need to constrain your model architecture and then data set. Okay, so we are about to complete the 5th epoch, and this is really far, just thanks to my RTX 3090. And now the 4090 has launched and it's much better in term of performance, but the GPU memory is same, I believe, 24 GB. So the training is done. Let's go back to our this file. So here you can see inside the files folder we have 2 files. First is log.csv. So let us open it. Okay, it's on the second desktop. So this is, here you can see we have all the values. First is number of epochs, so we have trained on 5 epoch. Then training accuracy, so we have got, and training accuracy 49%. Then we have training loss, that is 1.16. Then we have learning rate. After that we have validation accuracy, that is 48%. Then we have validation loss, that is 1.17. Next we have our weight file, that is model.h5, and you can see its size, it is really huge, 4.8 GB, and that is really huge for any model. Like, this is really huge, but training is not that like that time taking, also because the number of samples are less, that is also. But if we increase the number of samples, that may be difficult. Now let's finally test our model. So at least we get 50% accuracy within 5 epoch. Okay, let it done. Okay, we are hoping 50%. Yeah. Okay, we get an accuracy of 50%. We can see 5081 with the loss of 1.11. So you can increase the accuracy, decrease the loss by training it more, and you can apply data augmentation to further improve its performance. So that is all about image classification using vision transformer in the TensorFlow framework. So I hope you learn something from this video and you can use it in your project or in your research paper or anywhere you like it. So please subscribe the channel and hit that bell icon. Also, if you have any query, comment, any question, just put it down, and you can check the description for the link of the data set and also the code. Thank you. Have a nice day.